Hello, my name is Dustin Hoekstra with Cadence Design Systems, and today I'll be presenting my micro app on parallel and remote schematic simulation and optimization in the AWR design environment. Before I get into the specific topic, I just wanted to give an overview of AWR in case there's anyone unfamiliar with the AWR design environment. So to give a brief history, just so you know, it's primarily targeted at RF, microwave, and high-frequency circuit design. So basically, if you're familiar with the Smith chart, you're probably familiar with AWR. The applications are listed here: cellular, satellite, radar, electronic warfare. We do active devices like amplifiers and mixers, and then of course passive devices such as filters, antennas, etc. So things are, and in terms of the medium used, it would be semiconductors, most typically MMIC 3-5 semiconductors such as gallium arsenide and gallium nitride, RF PCBs, modules, and so on. So to look at the timeline of AWR, we can see we were founded in 1994. We've been in the industry for quite some time now. Some of the early highlights were the electrical physical co-design, meaning schematic and layout being not just in sync but sharing a common database. Moving on, we supported more and more EM, electromagnetic solvers. A key point in time was when we acquired a company called AWR to increase our simulation capabilities at the schematic level. And further on, bringing up all the way to 2020 is when Cadence acquired the AWR group, so just earlier this year, and that's why we see the Cadence logo on the bottom of the screen here. So if we were to put AWR into three categories or three buckets, you might say system design is one of them, where we have VSS, our system simulator tool, and that's more of the building a radio kind of level, where you're putting components together and using modulated signals to look at things like EVM, CCDF, ACPR. Now, what we're going to focus more on today is the circuit design and touch a little bit on EM analysis, but circuit design is really where we're focusing here. So that's where you have circuit schematics and layouts and the simulation of those schematics. And EM analysis is more for getting S parameters out of an electromagnetic solver. And going back real quick to this slide, the two electromagnetic solvers we have in our environment right now, or three if you count one from way back in the day, but the current ones are AWR AXIEM, which is a 2.5D 3D planar method of moment solver, and AWR Analyst, which is a 3D finite element method solver. And so here, just one other overview slide showing the application areas, as I mentioned before: MMICs, RF devices, and the strengths. One thing I'll mention here is the tuning and optimization and yield analysis. We'll touch on optimization quite a bit in this presentation, but that is something that comes into play quite heavily in the types of designs that we see. So let's take a little closer look now at parallel and remote simulation. So right now with AWR, as of May of this year, V15 is the current release. But if we go back a couple more releases, we can see we did support multiple EM docks. And when I say multiple EM docks, that means electromagnetic structures or geometries. Being able to simulate those remotely was very important, just because those simulations tend to take a long time. And we also supported swept EM docks. In V13, as noted here, this was included for remote simulation, but not for parallel simulation. And let me just get my laser pointer so it's a little easier to see. In V14, we did add schematic simulation for remote and parallel, because the demands of our users actually made it necessary for these simulations to require faster speeds. Normally, when you think of linear simulations, you're talking times of seconds or even nanoseconds or microseconds, but not usually a long time. But the complexity, which involves often bringing in S parameters with tens, hundreds, almost 1,000 ports and lots of frequency points, that can take some time to simulate. So that's what brought that about. And then in V15, we added EM extraction, and looking forward to beyond V15, and I'll show this on the next slide too, we might start to look at yield iterations and parametrically swept simulation docs. But really for today and what we have in the software right now, we're talking about multiple simulation docs and optimization iterations. And so those terms like simulation docs I'll explain in just a moment here. But before I get into that, I want to cover a few other useful definitions. So when we talk about remote and parallel, often the word distributed is used. And distributed can mean lots of things. So I really wanted to specify and define what we mean by parallel and remote. So as written here, parallel is referring to simulation on a single computer. For example, if you have a laptop that has 8 cores, you might be able to run 8 simulations in parallel on that one laptop. Now remote, on the other hand, would be simulating somewhere besides your own computer. So if I have a server farm with 6 servers or 6 machines to run on, that would be running remotely. And these aren't mutually exclusive, as I'll be showing a little later on. And then a job. What's a job mean? Well, it's a simulation document. So a simulation document might be a schematic, might be an EM structure, might be a data file or a net list, but what we're focusing on today would be the circuit schematics with a little bit of background in reference to EM structures. So to give a better visualization of what I just spoke about in the previous slide, here we can talk about a single simulation job. So this is one schematic, one job. We hit go and it takes 52 minutes. And so we want that to run faster, obviously, so we can parallelize it locally. So if we ran it on this multi-core computer and did 3 parallel jobs, we can get it down to 36 minutes. However, we can also take the approach of doing it remotely. So if we do it remotely on 6 different computers with just one job each, and once again a job is another word for a simulation of a circuit in this case, that can get it down to 12 minutes. And then if you combine both of those and did 6 different computers or 6 nodes and 3 parallel jobs each, we can get it down to 6 minutes. So you can see quite a bit of improvement there. And this is just one example. We've seen much greater improvement in other examples too. These were just some lead user examples we're showing here. So to look at the kind of the 4 different ones, and as I mentioned, we're discussing EM simulation as kind of a reference. So for an EM simulation on a local computer, you might go from 105 minutes down to 18 minutes. And let me elaborate a little bit more on this annotation here. So we see 1, 1, 1, 2, 6, 1. And just to make it clear, that means number of remote machines and number of parallel machines. So if we were to look at, say, this optimization that ran in 6 minutes, that was 6 different computers and running 3 jobs per computer. So for a total of 18 jobs. So for that optimization, it went from 52 minutes down to 6 minutes. And the one right above it, it was multiple circuit schematics, 44 minutes down to 9 minutes. And you can see things gradually decrease in general, but however, one might notice that sometimes these times go up. Right here, for example, and what that can be is a result of not having enough memory resources on that single computer, which is why running remotely will get you a better advantage. And if we look at this nonlinear swept circuit schematic, we see it even gets worse for both, and with seeing a minimal advantage in remote parallel. And the reason for that, as is described down here, is that swept circuit schematics don't show much benefit for this one because of the iterative harmonic balance solver, an incremental linear solver. So when you have an iterative solver, it relies on previous results, and if you distribute that, you might lose that advantage. That doesn't mean that it cannot be beneficial, but we wanted to point out that it doesn't solve all your problems always. You have to put a little bit of thought into what kind of problem you're putting towards this type of approach. So to kind of show a picture of how one would run parallel optimization, so this is just parallel, keep in mind, just for one computer, you would go to our optimizer window, which for those of you who are familiar with AWR would know this window well, where you choose from a long list of different optimizers. And as of V14, which was the most, not the current release, but the one before it, we had 3 parallel solvers available. And just brand new in V15, we added another one called Kapu. And here, once you choose one of those, it lets you set the number of parallel jobs. So say I had a 4-core computer, I might set this to 4. And that's just on that one computer. However, to show another example, so say we wanted to run multiple schematics, so not just an optimization, but just running these 4 schematics. Say each of these took 5 minutes to run. So if we wanted to get things done faster, we can run it on a remote machine. So run those 4 schematics on A through D. So schematic 1 goes to A, for example, 2 to B, 3 to C, etc. So that would run considerably faster. And then if you say had 16 schematics, and then you wanted to run those all at the same time, you could send them off to A, B, C, and D and have them run in parallel on each of those. And just a little graphic here to show how you might set something like that up in AWR. So with all these benefits shown, I'd like to quickly explain how this would work from a licensing perspective. So we talked about EM a little bit. AXIEM and Analyst are EM solvers. So those, as I mentioned before, have been around a while, and those use something called tokens to run remotely. So 2 tokens for AXIEM, 4 tokens for Analyst. For remote circuit schematics, so that's sending your simulations of your schematics to other computers, it uses your startup features. So if you have a Microwave Office 200 on your computer, it requires a 200 on the other computer. And if you want to parallelize, so maybe just on one computer running 4 jobs, you need 2 tokens, called token 200 in this case, to differentiate it from the EM ones for each parallel job that goes beyond what you're already simulating. So set that up on different computers, you multiply them, etc. And for nonlinear, it's just 4 tokens because that's a more complex type of simulation. So that pretty much covers things. Just to review real quick, I'll go back a few slides. So we can see the real benefit of running these types of simulations. When things take up to this level of time, almost an hour, it's great if you can get it down to 6 minutes by just adding compute resources. Because as we know, an engineer's time is valuable, and compute resources compared to that might be a lot less, and are things that are shareable. And basically getting the results faster is an excellent goal for any software. So we found a way to do that using a few different options and being able to combine those options. So I appreciate your time, and thank you for attending or watching my video.